Hi, welcome back to AP Physics C, Unit 5. This is the last video for this unit. Um, and it seems like we went through this fast, but we didn't because there's a lot of connection between units 1, 2, 3, 4, and this unit, right? The only difference is that we're changing the variables, right? And which changes our units, but our applications are going to be the same, okay? So here in this video, we're going to look at angular momentum. So remember that there are three conserved quantities in mechanics, right? Energy, which we talked about in Unit 3, linear momentum, which we talked about in Unit 4, and now we're finally going to talk about the third one, which is angular momentum, okay? So again, you can see there's like an analog, there's a connection between linear versus angular, but we're just applying it just a little bit different, right? We're not moving in straight lines. We're moving in, rotations, okay? So angular momentum is the rotational analog to linear momentum. And there's various ways to kind of calculate some of this. So the basic way to calculate linear or angular momentum is I times omega, right? If you remember, momentum is P equals mv, right? But so L is our angular momentum. I is our rotational equivalent of mass, and omega is our rotational equivalent of speed, right? Velocity. Now, sometimes a question may involve like a point mass rotating, and it doesn't necessarily give you this kind of information, but the angular momentum of a point mass is simply mvr, right? So it's the momentum times the radius at which it is applied. And we're going to look at an example problem using this, but a lot of times it'll talk about like planetary motion and ask you for the angular momentum of a planet in motion. They may ask you about, you have a merry-go-round spinning and then someone jumps on it at a certain point, right? Or, a merry-go-round is not spinning and then, a person jumps on it, which is going to then causes it to rotate. That's kind of the example we're going to look at. But there's different types of things that we could apply here. So 1 point mass example would be planets. And the other would be like if I have someone running towards this merry-go-round that's going to rotate, they jump on it, right? And now they start rotating, okay? So it is an inelastic rotational collision, okay? Which then here on this side, you would need to find a total I, right? Versus having to find a just using the I for the moment of inertia for the disk is what it amounts to. Now, I know we didn't talk about, there are some common moments of inertia that you need to remember. I'll put in the comments what they are so that you guys can have those available to you. And AP only looks at some of them where, if you're taking this as a college course, they're going to look at more, okay? Just like when we talked about momentum, we have an angular impulse, and that's equal to our change in angular momentum. It's all the same, right? It looks like the impulse momentum theorem equation, and it basically is, right? But then we can also do some calculus, right? So torque dt, or right, the integral of torque dt, or tau dt is our, so what does that mean? If we have a torque versus force or torque versus time graph, right? Just like we have force versus time, that's our angular impulse, okay? And then angular momentum, right? We said it was a conserved quantity, which tells us that the change in our momentum is equal to 0. And a couple examples that they like: spinning a disk and dropping another one on top of it, and then our figure skater, right? Those are some very important ones. So like with our figure skater, her moment of inertia, right, for when she's got her arms out is big, which means she has a small angular velocity. But when she tightens up, and brings her arms in, she decreases her I, which causes her omega to go big. Okay. And that's why, when you watch figure skating, when they spin, when their arms are out, they're spinning slow. And then when their arms are in, they're spinning faster. And the reason why is because when you put your arms out, you're changing your distribution of your mass that's spinning away from the axis of rotation. Okay. But then when you bring it in, it's tighter to the axis of rotation. Okay. So now let's look at an example problem of where it's going to be the example where we kind of the merry-go-round where someone's going to jump on it, but we're going to use a bullet to rotate a disc. So a bullet of mass 2 grams is moving horizontally with a speed of 500 meters per second. The bullet strikes and becomes embedded in the edge of the solid disc of mass 3.2 kilograms and radius of 0.5 meters. The cylinder is free to rotate around its axis and is initially at rest. What is the angular velocity of the disc immediately after the bullet is embedded? Okay, so the way we look at it is we have a before and after, right? Or so we'll back it up real quick. So the moment of inertia of a disc is 1/2 mr squared. But the bullet becomes embedded in the disc, so we have to find the total after. So it's going to be 1/2 mr squared. And we just treat that bullet as a point mass. So it's going to be plus mr squared, right? And so when I plug in the numbers, it's 1/2 times 3.2 times 0.5 squared plus 2 times 10 to the -3, because it gives it to us in grams. We need it in kilograms, times 0.50 squared. And so my moment of inertia is 0.4005. Now I need that for the after scenario because now I've got the bullet with the bullet inside the spinning disc. And so now I can say delta L equals 0. Let me change the color. So what does that mean? My final L minus my initial L is going to equal 0. And that just means my final equals my initial. Now, this is where we're talking about the bullet is not rotating, but it causes rotation. So its angular momentum is simply mvr. So we'll call it mass of the bullet. But over here, we have the total I times omega. And we're solving for omega. So it's going to be mv, mass of the bullet, vr, over the total moment of inertia after the collision. So it's going to be 2 times 10 to the -3 times 500 times 0.5, right? Because if you look, it is taking a direct line to hit the outside, right? So it's, if I'm looking top down before, here's my radius, and so the bullet is going to be traveling in that direction. So it is technically 0.5 meters from the axis of rotation. And then I'm going to divide it by that 0.4005 number. So my disc will now be rotating at 1.25 radians per second. All right, so that's the end of Unit 5. We will look at Unit 6 next, which is oscillations. The next 2 units are going to be very short and quick because that's how they are presented on the test. They're the 2 smallest units on the test, and that's why they kind of get stuck here at the end of the curriculum. So looking forward to your adventure here in Unit 6.